All right, Fabian, we are live on Zoom and live on YouTube.
All right, so are we ready to kick off, Humam?
Yes, go ahead. Do you want to wait maybe a couple of seconds more? I think that we're still having participants.
Okay, great. So let me know when you see people start joining the room so we can go ahead and start.
Welcome, everybody. We will start soon. Just waiting. All right, Fabian, you can go ahead.
Okay, welcome everybody to the 6th edition of the International Challenge on Activity Recognition at this CVPR 2021. We're happy to see you all here virtually, and hopefully next year we will see you in person. And I want to start by introducing our challenge organizers, starting with our program chairs. So this year we have a good mix between academic and industry program chairs, and we have do this in purpose to actually bring different perspective about the video understanding challenges. Also, I would like to thank all the challenge organizers, including Frost Shu, Humam Alwassel, Ranjay Krishna, Shaimal Book, and all our guest task organizers. Without your help, it wouldn't be possible to host this challenge this year. Thank you a lot. Again, just a quick reminder about what the activity in the workshop is about. Our goal is actually create a community and enlarge a community where people discuss topics about understanding video and understanding what people do in videos. For instance, some of those challenges is understand what actually is happening in a video, but also where is it happening in time and space. Also, another challenge is to describe what people is doing in those videos with natural language. This year, we're happy to share that we host 12 different challenges in different areas of video understanding. That includes action recognition, temporal localization, spatial temporal detection, complex event understanding, and multi-view and multimodal video understanding as well. In terms of the program, so we will be hosting 2 keynote sessions today. So we will kickstart with the morning session. We will have Gedas from Facebook and Jean-Baptiste from DeepMind. So stay around for their talks. They are going to come after me. And then in the afternoon session at 3 p.m. PDT or Pacific time, we will have Carl Bondrick from Columbia and Huyam from Berkeley. So please join us in the afternoon session as well to learn more about their works. So we will have also pre-recorded sessions for each of the challenges that I just mentioned before. So please make sure to join our YouTube channel where you will find all the information about those challenge sessions. So with that, I let the space to Humam for introduce our keynote speakers and the logistics of the Q&A session at the end.
Thank you, Fabian. So we will have the keynote session, the morning session now, and we will have the afternoon session. The setup is that we will allow Q&A option. So on the Zoom link, if you look at the bottom, there's a Q&A. You can ask questions there to the speaker at any time. Fabian and I will filter these questions and ask them directly to the speaker. And you can also watch this webinar on YouTube. So I have posted on the chat the link to the YouTube live. And with that, I will introduce our first speaker. So our first speaker is Gedas. He's a postdoc researcher at Facebook AI. His recent works in video transformers have generated splash in the vision community. We are glad to have Gedas today with us on stage and talking about the time transformer work. Gedas, you can start.
Can you guys see the screen? Sorry, I was muted.
Yes.
Okay, yeah, so thank you for the introduction. My name is Gedas Bertasius, and today I'll be presenting our latest work called Is Space-Time Attention All You Need for Video Understanding? And this is a joint work with Heng Wang and Lorenzo Torresani, both from Facebook AI. So in this work, our main focus is on a supervised video classification task. Given a video, we want to classify it into one of the human action categories, as is shown in this slide. And before I start describing our model, I wanted to take a step back and briefly talk about the modern language models which serve as an inspiration to our model. So as you're all probably familiar, in the last few years, the field of natural language processing has been revolutionized by the self-attention-based models such as the transformer model. Their simplicity, their ability to learn from large-scale data, and most importantly, their ability to model long-range dependencies in the data is what makes them so appealing and so powerful. And at the moment, these self-attention-based models define state-of-the-art for most natural language processing tasks, such as question answering, machine translation, text generation, and so on. So why do we care about the modern language models or self-attention? Well, we care about it because at a high level, video understanding and natural language processing share several similarities. For one, both videos and sentences are fundamentally sequential. So you would think that whatever model works well for text also to some degree should generalize to video understanding tasks as well. But second, even more importantly, we know that a lot of times in order to understand the meaning behind individual words, we have to look at a broader context and we have to look at an entire sentence instead of individual words. And similarly, you could argue that in order to understand atomic actions in short video segments, we also need to leverage broader context and we might need to look at an entire video. And because of these reasons, we believe that these long-range self-attention-based models should also be highly effective for video understanding. However, most state-of-the-art video classification methods currently rely on some form of 3D convolutions for spatiotemporal feature learning. And we argue that self-attention has several important advantages over 3D convolutions. So for one, we know that the self-attention mechanism imposes fewer inductive biases, which renders self-attention-based models better suited to modern big data regimes. Second, we know that 3D convolutional kernels, they're inherently designed to only capture short-range spatiotemporal dynamics. And in contrast, the self-attention mechanism is much more flexible since it can capture both local as well as global long-range dependencies in the data. And lastly, due to the large computational cost of modern 3D CNNs, it's quite difficult to scale their model capacity while also maintaining efficiency. And prior work has actually shown that it's quite easy to scale these self-attention-based models. So motivated by these observations, our goal in this work is to design a video architecture built exclusively on self-attention. And to do this, we leverage the framework of a recently introduced vision transformer, which achieved impressive results on image classification. So specifically, we viewed the video as a sequence of non-overlapping frame-level patches. Each patch is then linearly mapped into a feature embedding, which is then augmented with spatiotemporal position information. And this basically allows us to interpret the resulting sequence of feature vectors essentially as tokens that can be fed into the transformer encoder, analogously to the tokens computed from words. However, one downside of a standard self-attention mechanism is that it requires computing similarity measure for every single pair of tokens. And in our setting, this is very computationally costly due to the large number of patches in the video. And so this brings us to the main focus of our work, which is to design scalable space-time self-attention scheme. And so the first question that I'm going to focus in this talk is, what is the right space-time self-attention pattern in this case? And what I mean by right is that we want something that's both effective and also efficient. So in this case, we investigate 5 different self-attention schemes, namely space-only attention, joint space-time attention, divided space-time attention, sparse local global attention, and then lastly, axial attention. So let me try to describe each one of these in more detail. So let's start with the space-only self-attention. So here, what I'm visualizing, this blue patch, it essentially depicts a query patch for which, in this case, we want to compute a self-attention-based representation. And so, of course, in practice, we want to do this for every single patch. But here, just for illustrative purposes, I'm focusing on this individual case just so that we could understand the differences between each of these self-attention schemes. And all these differently colored patches, so these red patches, they indicate the self-attention neighborhood. So basically all the patches for which we will need to compute a similarity measure with respect to this blue query patch. And so as you can see from this illustration, because this is a space-only self-attention, we're only considering patches that appear in the same frame as this blue query patch. And the advantage of this scheme is that now we don't have to compute similarities for every single pair of patches, which makes the scheme much more efficient. But the disadvantage is that now we can only consider spatial dependencies in the data, which clearly is suboptimal for many video understanding tasks. So on the other end of the spectrum, we have this joint space-time self-attention. And this is just a standard self-attention implementation where now we're considering every single pair of patches. And the advantage of this is that now we can do full spatiotemporal modeling. But of course, as already discussed, the disadvantage is that now we have to consider every single pair of patches, which is very computationally costly. So to address this computational efficiency related issues, we propose a divided spacetime self-attention. And here the key idea is very simple. We simply factorize this joint spacetime attention into its 2 components, into temporal and spatial attention. The spatial attention is implemented in the same way as before. So we're simply considering patches that appear in the same frame as this blue query patch. But now we also have this temporal attention depicted by these green patches. And so now we're also considering patches appearing in all the other frames in the video, but only patches that appear at the same spatial location as this blue query patch. And so basically then the model separately applies temporal and spatial attention one after the other within each block of a network. And this allows us to do both spatial and temporal modeling. And at the same time, we don't have to compute similarities for every single pair of patches, which makes the scheme much more efficient compared to the joint spacetime attention. Another scheme that we consider is this, what we refer to as local global self-attention. And here the key idea is to basically more efficiently factorize this joint spacetime attention. And so here, basically, as a first step, what we do for every patch, we first compute a local attention by considering a small spatiotemporal neighborhood around this blue query patch. So these are indicated by the yellow patches in this case. And as our second step, we then compute a sparse global attention over the entire video clip with a stride of 2. And so these are indicated by these purple patches. And so as already said, this can be viewed essentially as a faster approximation of this joint spacetime attention, where we have this local global decomposition, and we also employ the sparsity pattern. And lastly, we also consider this axial attention. And the key idea here is to decompose the attention computation over 3 axes, over time, width, and height. And so these axial self-attention schemes, they have been shown to be pretty effective in the image domain. And so here we also want to experiment it in the video domain. And so it's easy enough to do it. We simply have to extend this scheme basically to incorporate time axis. And so that's what we do. So those are the 5 schemes that we consider. And next we evaluate each of them on 2 popular action recognition benchmarks, namely Kinetics 400 and something V2. And so here, following the basic vision transformer setup, each of these baselines is pre-trained on ImageNet 21K dataset. So here, based on these results, we observed that among the proposed design choices, our divided spacetime attention scheme, which separately applies temporal and spatial attention one after the other, it performs best on both datasets. And so interestingly, we actually observed that it actually performs even better than the joint spacetime attention And this is a little bit strange because it was only supposed to approximate this joint space-time attention scheme, but now we see that its performance is actually better. And so one of the reasons why this is happening is because, as you can see, this divided space-time attention scheme, it actually has much larger learning capacity. So it has a lot more parameters than the joint space-time attention scheme. And in a sense, this allows it to model spatial and temporal information separately, which gives it more representational power. But so now you might be wondering, okay, yes, we get a boost of about 0.5% on kinetics and about 1% on something V2, but we also have these additional 40 million parameters. So is it really worth it? And interestingly, we note that even though this divided space-time attention has a lot more parameters than the joint space-time attention, in practice, it's actually much more efficient. And so here we plot the computational cost measured in terms of T-flops as we increase the spatial resolution of the video, which is a plot on the left, or if we increase the video length, which is a plot on the right. And here, based on these results, we observe that our divided space-time attention scheme, it scales reasonably well in both of these settings, as illustrated by these blue curves. Whereas the joint space-time attention scheme, its computational cost grows pretty rapidly to the point where we can't even use it because it simply runs out of GPU memory. And so these experiments validate our design choices because we now have this divided space-time attention scheme that achieves the best performance on both of these action recognition data sets. And it's also much more efficient than the joint space-time attention. So for the rest of the experiments, we build our model using these divided space-time attention blocks. And so next we focus on our second question, which is space-time attention actually better than the previously used 3D convolutions? And to answer this question, we conduct an empirical study aimed at trying to understand some of the distinguishing properties of our model, which we named Timesformer, from time and space transformer, compared to these previously used 3D CNNs. And so in here, for our comparison, we focus on two distinct 3D CNNs, namely I3D and SlowFast. And so based on these results, we observe a few interesting differences between these two types of models. So first, we observed that our Timesformer model has a very large learning capacity, which is indicated by a large number of parameters, so almost 120 million parameters. At the same time, despite having this many parameters, as you can see, its computational cost is relatively low. So it has the smallest computational cost among all of these models. And in contrast, when we look at 3D CNNs, we observe a very different trade-off between this inference cost and the number of parameters. So we see that the 3D CNN model capacities are much smaller than for our Timesformer model, so 3 to 4 times smaller, but also they have a higher computational cost. And so these results indicate that our Timesformer model might be much better suited for large-scale learning. And in contrast, these 3D CNNs, it's quite difficult to scale their model capacity while also maintaining efficiency because they're already quite computationally costly. So the second finding that we observe is that, well, it's definitely nice that our model has a large learning capacity, but it also comes with some disadvantages. And so specifically, we observed that it's quite difficult to train our model from scratch. And as a result, we have to use this ImageNet level pre-training. So here we experiment with two different kinds of pre-trainings, ImageNet 1K and a larger version of ImageNet 21K. And we observed that in this case, using this larger version of ImageNet 21K leads to about 2% boost in performance on Kinetics 400. And these results are relatively consistent with what was discovered in the image dummy, where it was also shown that these transformer-based models, they're quite data hungry and they perform much better if you train them on a lot more data. And so, while this is certainly one of the limitations of our model, that we have to rely on this ImageNet pre-training, but it also comes with some positives. And so specifically, we observed that ImageNet pre-training enables very efficient training of our model on the video data. So specifically, we see that on Kinetics 400, it takes just about 15 epochs to train our Timesformer model, which corresponds to about 416 GPU hours. And even with such a short learning schedule, we can still obtain a pretty good accuracy. And in contrast, when we look at 3D CNNs, we observe a very different trend. So even if both of these 3D CNNs, I3D and SlowFast, are initialized with ImageNet 1K, they still require a very long and slow optimization schedule. So specifically, we see that for SlowFast, it takes about 3,800 GPU hours to get to 75.6% accuracy. And for I3D, it takes about 1,400 GPU hours to get to even lower, 73.4% accuracy. And if we constrain these models to have a somewhat similar computational budget as our model, and all models being pre-trained on ImageNet 1K, we see that the performance of 3D CNNs drops quite significantly. And so this highlights this overlooked fact that a lot of these modern 3D CNNs, they perform well, not only because of the model design choices, but even more importantly, because of this very long and slow optimization schedule. And in contrast, our model doesn't need that, and it can be trained quite efficiently. So the next question then that we focus on is, what is space-time attention particularly useful for? So one of the exciting characteristics of our transformer model is that we observe that it can operate on much longer video clips compared to most modern 3D CNNs. So here we observe that our model achieves the best performance when operating on video clips consisting of 96 frames. And this is a significant departure from these modern 3D CNN models, which are typically limited to processing video clips consisting from 8 to 32 frames. And so to further evaluate our model's ability for long-term video understanding, we introduced a new benchmark using the recently introduced How to 100 Million dataset. So How to 100 Million dataset is a large-scale instructional video dataset that contains more than 1 million clips demonstrating humans performing a variety of different tasks, such as repairing a car, making dinner, cleaning a house, and so on. And the nice thing about these videos is that on average, each video in How to 100 Million lasts for about 7 minutes in length, which is orders of magnitude longer than videos in standard action recognition benchmarks such as kinetics, which typically last for about 5 to 10 seconds. And second, each of the How to 100 Million videos also has a label indicating which of the tasks a human is performing at that in that video. And so we can use these labels for supervised training in this case. And so because of these, we believe that this is a very good benchmark to assess a model's ability to recognize activities exhibited over very long temporal extents. And so we construct this new benchmark consisting of 120,000 videos spanning 1,059 long-term action categories. And then we train our model on this new benchmark. And so here as our baselines, we use 4 variants of slow fast operating on a different number of clips, a different number of frames. So specifically 8, 32, 64, and 96. And we also use the same 4 configurations for our transformer model. And during inference, for each method, we sample as many non-overlapping temporal clips as are needed to cover the full temporal extent of a video. So for example, if a single clip covers about 8.5 seconds, then we would need to sample 48 test clips to cover a video lasting for about 410 seconds. And so then the final predictions are obtained by averaging all of these clip level predictions. And so based on these results, we observed that for a fixed single clip coverage, our transformer model outperforms slow fast by a pretty substantial margin, ranging from 8 to 11%. And this indicates that this space-time attention mechanism might be much better suited for long-term video understanding compared to these previously used 3D convolutions. And second, we also observed that longer range transformers actually do better on this benchmark. So we see that the best performance is achieved by transformer operating on 96 frames. And this again indicates our model is able to aggregate all of these long range temporal cues and leverage them to maximize the performance on this benchmark. And I think this is a very exciting finding because up to this point, there's been some work on long-term video understanding, but in my view, it's been largely overlooked. And we're hoping that our work will open up more opportunities to do research in this area. And so lastly, I wanted to finish this presentation by posing this last and probably the most important question, which is space-time attention all you need for video understanding? And instead of giving you a direct answer, I just wanted to summarize our findings so that you could form an answer by yourselves. So as for the advantages of our model, as I already mentioned, compared to modern 3D CNNs, it has a much larger learning capacity, but at the same time, you can design our model such that it has a comparable or even lower inference cost. And I think this is very useful for larger scale data settings, and this is where our field is going. So I think these transformer-based models are going to be more and more important. Second, we also, as I discussed, one of the benefits of our model is that it doesn't require this very long and slow optimization schedule, unlike 3D CNNs. And I think this is important because video understanding is already a very computationally costly area. And so even with Facebook level resources, it's quite difficult to train these 3D CNNs from scratch. And so we're hoping that this will make things a little bit easier because our model can be trained much more efficiently on the video data. And third, probably the most exciting finding for me is that our model can operate on much longer videos. And again, as I mentioned, I think this can open up new opportunities for tasks and research and geared towards long-term video understanding. As for the disadvantages, so due to a large number of parameters, currently our model still requires image level pre-training, which of course is suboptimal, and that's something we want to eliminate. And also we observed that on temporally heavy data sets, such as something v2, our model actually performs worse, substantially worse than state-of-the-art. And this clearly indicates that some improvements are still needed for temporal feature learning. And so having said this, while these disadvantages, we identified them very soon after publishing the paper, at the moment, the field is moving so fast that it seems that many of them have actually been already addressed. So on the fact that our model relies on this ImageNet pre-training, in our follow-up work, we actually showed that self-supervised pre-training can be a very effective alternative to this large-scale supervised ImageNet pre-training. So here we introduce this long, short temporal contrastive pre-training scheme, and we showed that we can actually outperform our own model that uses this large-scale ImageNet 21K pre-training. So now this reliance on ImageNet pre-training is essentially eliminated. As for the more effective temporal feature learning, there's also a recent follow-up work that shows that they introduced a new trajectory attention-based mechanism, and the authors in this paper showed that it's quite effective at learning more effective temporal features. And so as you can see, whereas our transformer model was lagging a bit on this something v2 data set, this new model MotionFormer actually sets new state-of-the-art on this benchmark. So it seems that both of these issues have actually been addressed. And so with that, I wanted to say that also our code and models are publicly available at the following GitHub repo. And also, if you're interested, definitely check out our paper. It has a lot more details and also a lot more experiments than I was able to present in this talk. And so with that, I'd be happy to answer any remaining questions. Thank you.
Thank you, Gedas. People can ask questions on the Q&A. And if you feel okay with raising your hand and asking it in person, also click on the raise hand.
Thank you.
Go ahead,
meanwhile, people.
Dwayne. Dwayne, are you here? Okay. Fabian, if you have a question, you can go ahead.
Yeah, so meanwhile, people ask their questions. So I have one question, Gedas. So do you think is there any limitation of the method? I mean, first of all, thank you for the presentation, great presentation. But do you think there is like any limitation in terms of like the video source you can use for pre-training TimesFormer or MotionFormer? So for instance, like, do you need to have videos that are like unedited or like that doesn't have any shortcut between them? Or do you think still these methods will work for this type of video sources, right? Where you have a lot of editing, a lot of like cuts, maybe the information is changing across shots and things like that. I think that's still suitable for learning or for training these methods.
I think, I mean, it's difficult to say, you know, without any empirical evidence, but I would say, I guess I don't see them maybe being worse than, you know, what we currently have. Yeah, so I think, you know, it would be interesting for sure to get some empirical evidence on this and to see, but yeah, I guess like I don't see any reasons why they wouldn't work. I think currently, you know, so one of the big limitations, as I presented initially after publication of our paper, is that, you know, we very heavily relied on this ImageNet pre-training, which obviously biases representation that you're learning, you know, on whatever video data you're training it afterwards. But so I think now we kind of showed that, I guess, like with self-supervised learning, you can sort of eliminate the reliance on this ImageNet pre-training. And so I think it makes the model much more flexible and, you know, probably, yeah, more suitable for any kind of data set. Yeah.
Yeah, thank you.
All right, so we have one question from the audience from Cecilia. She asked, did you try on ActivityNet? Did you also get good results on it? Is it easy to optimize? And they mentioned that they tried the code, but they didn't get any good results on ActivityNet.
Yeah, so actually, so I did run a few experiments on ActivityNet. Actually, I think in terms of optimization, so I think it's very easy to optimize our model because for all data sets, I didn't even change any hyperparameters. So basically whatever is in the code base, we use it for any data set. So I actually didn't have any optimization issues. And in terms of ActivityNet, so I basically tried it on the just like ground truth proposals for video classification. So instead of just feeding these long untrimmed videos, just basically using trimmed videos as our input. Actually, yeah, we were able to get very good numbers. Yeah, I would need to look actually at the and at all of my results, but I think it was close to like 90% accuracy. Yeah, like with the longest term video. So I think ActivityNet is really well suited for our model because so this like 96 frame model, it's very well suited for long-term videos, and ActivityNet videos, most of them are pretty long. Yeah, so we were able to obtain pretty good accuracy just like on these ground truth proposals for action recognition.
Awesome, awesome. Maybe another question from me. Have you tried any other application on the self-supervised direction?
Yeah, so we're still, I guess, like, yeah, so in this latest work here, basically I referenced to, so it's mainly, our main goal was to kind of eliminate this ImageNet level pre-training. And so that was kind of the main goal. But of course, in practice, I think these transformer-based models, they become much more suitable for multimodal learning because now, you know, all of these language models that we have, they're also transformer-based. And actually, I've already seen some work coming out, that basically uses it for video retrieval, just like learning these multimodal representations. So maybe not exactly in self-supervised learning, but some sort of, you know, weakly supervised learning where you have you know, pair text to the videos, and it just becomes easier, you know, to model, to learn joint representations for video and text using these kind of unified transformer models.
Thanks. Any last questions from the audience? All right, let's thank Gedas. Thank you so much for the talk. Our next speaker is Jean-Baptiste. Jean-Baptiste is a research scientist at DeepMind. All right, just give me a second. He has done some works on self-supervision, specifically on the multimodal settings. He will talk to us today about his recent research on self-supervised multimodal networks. Jean-Baptiste.
Hi everyone, can you hear me?
Yes, go ahead.
Yeah, and do you see my screen? It's good?
Yes.
Great. Cool. So yes, hi everyone. So I'm Jean-Baptiste and I'm a research scientist at DeepMind. And today I'll share some kind of work and reflections around kind of getting towards more versatile and more powerful multimodal networks. So first of all, like why multimodal? Why should we care about multimodal? But like first of all, it's because our world is multimodal. So if you go like outdoor, you will have like visions, you will have audio coming through, maybe people will talk to you with language. And if we want to really have models that are that can be adapted to the real world, we need them to be able to run on those multiple modalities. And just to make this a bit more concrete, I'll just play a little video to illustrate the importance of multiple modalities in our video understanding.
Get as close to the root as possible. Nice, long stroke. Get.
I'll just play it again.
As close to the root as possible. Nice, long stroke.
So in this video, there are multiple signals. So first, there is the chef demonstrating how to kind of cut this onion. But there is also the kind of audio track where you can hear
and try to get
the sound of the knife on the cutting board.
Nice, long stroke.
But also from the audio, like the chef is giving you instructions with language that you can understand. And this kind of instructions can be transcribed into texts using methods such as automatic speech recognition to kind of get in the form of text what is contained in the speech. So you can see already that with the simple video, there are like three sources of signal, like the visual signal, the kind of audio content, like the sound of objects, as well as any communication that can go through the language via the audio signal. And basically, in this work, I'm going to try to argue that we need to go towards more multimodal approaches and what we should expect from those multimodal networks. So I kind of want to talk about 2 points about multimodal networks. I want to focus on versatility and the power of those models. So in terms of versatility, there are like 3 aspects of it. So first, a good multimodal network should be able to take as inputs multiple modalities like audio, video, and language. It should also be able to easily relate modalities together. For example, when you hear the sound of the knife, you know it's associated with the appearance of the knife. So we want to have this kind of similar behavior in our models. And also one important aspect is that we want our models to not only be good at videos, but also being able to kind of consume in an efficient way just still images. Like for example, in our case, we kind of learn from this continuous stream of data, but we are able to kind of just look at pictures and understand what's going on. But we don't want them to be only versatile. We also want them to be kind of powerful. And what do I mean by that? I mean that those models should be able to learn from large amount of unlabeled and uncurated data. And also we should have like rich interactions between the different modalities. So not something very simple, but we want to be able to kind of merge the different modalities with rich interactions. And also we want them to be fast and efficient. And today I'll try to share 2 works that kind of go towards that, in my opinion. So the first one is work that we did last year at NeurIPS, which is called Self-Supervised Multimodal Versatile Networks, and which try to learn multimodal representations from video, audio, and language contained in large collection of uncurated data sets. And in the second part, I'll present a work that will be presented this next week at CVPR, which is called Thinking Fast and Slow to Improve Text-to-Vision Retrieval. And there, I'll focus more on the vision and language aspect and see how we can make our model more powerful while still keeping while still having them very fast. So with this introduction, let me start the first presentation about our work called Self-Supervised Multimodal Versatile Networks. So what's the motivation and kind of the research questions beyond this work? So what we want to do is really being able to learn in a self-supervised way, so without kind of human labels, on multiple modalities naturally present in videos, which are vision, audio, and language. And we will have like two main questions towards this talk. So the first one is, are 3 modalities better than 2 for learning and for improving on downstream tasks? And also, what kind of architectural designs are going to give benefits beyond performance? And the main idea of the work is pretty simple, and it's actually quite an old idea, which will consist in kind of embedding the different modalities in a kind of joint embedding space. So for example, you can take the audio raw signal, embed it with a network into a space, do the same for the visual signal, same for the language, and you can embed all of those kind of modalities in the same space. And you can do the same for a different video. And now you can use the fact that all the modalities coming from the same video are kind of related together. So for example, on the left, you have this guy playing the guitar. He will most probably play the guitar, so you will hear the sound of the guitar. And he might say something about I'm playing the guitar, so the language information might already be there. So in terms of the learning signal, what we can try to do is to try to learn the representation so that the modalities coming from the same video are going to be close together. And they are going to be close together compared to some negative videos. So for example, if we take the video from this example, the guitar, we want them to be close from its own audio, but relatively to kind of audio coming from other videos, such as the one I played before. So we'll have this concept of positive and negative pairs, and we'll use contrastive learning for that. And I'll go in more details later on. So there are lots of related work that kind of leverages the same ideas. In vision, I think one of the most famous one in the last year is SimCLR or SimClear, which kind of uses kind of technique with images alone, so single modality. People have also looked into vision and text in past work, and also vision and audio, including the work from Humam here. But this work will focus on having like 3 modalities and not just 2. And also we'll focus on this kind of versatility aspect, and I'll just kind of describe this checklist that we have for our models. So first, we want that our model can take any of the 3 modalities as input. We want them to be able to respect the specificity of modalities, and I'll come back a bit later to what I mean exactly by this. Third, we want to enable the different modalities to be easily compared. So we want, again, to be able to understand that the appearance of the knife is related to its sound on a cutting board, for example. And finally, we'll try to describe an approach to be able to kind of learn from video, but directly adapt those networks to images in an efficient way. So I'll start with just the first 3 properties. So first question is like, how do we obtain those embeddings that I described before for each of the modalities? So one question that comes to mind is like, should all modalities be embedded in the same space, or should we have like specific spaces for the different modalities? And in particular, like having different spaces might be interesting to kind of respect the specificity of modalities, because for example, like when you compare audio and video, like the kind of signal you will compare might be much more fine-grained than when you compare to language. Because, for example, for guitars, there are many sounds of guitar, but a single word to describe guitar. And we will explore those questions by designing different network architectures that we call embedding graph design. And I'll present you just 3 options that we considered, and there are different pros and cons. So the first option is to have this kind of shared space, which is probably the most natural option at first, where, as you can see here, we can embed the audio, the video, and the text all in the same space, and we can compare them together via simple dot products. So this kind of approach enables you to kind of compare the different modalities easily, because you can compare the video and audio, the video and text, but also you can compare the text and the audio, even though, like it will be our case in this work, we don't have explicit audio and text pairs during training, but you can still compare them afterwards because they are kind of living in the same space thanks to this kind of shared video signal. But so this is nice in the sense that you can kind of compare all those modalities easily, but also it's a bit not ideal because you treat all those modalities as if they were equal. So like this kind of argument I gave earlier about the sound of the guitar and the single word for the word guitar, this approach kind of treats all modalities as if they were the same. So a second option, which is kind of the opposite of that, is to allow a specific treatment of the different pairs of modalities and basically have different kind of spaces for the video and audio comparison and the video and text comparison. So that's what we call the disjoint spaces. So this is good because it allows a specific treatment of pairs of modalities, but in the same time, it's now not easy to compare modalities, notably in the setting that I described earlier, where we won't have like audio and text pairs together during training. Because in this case, like we have a specific branch for comparing video and audio, a specific branch for comparing video and text, but we don't have an easy way to go from text to audio. One way could be to invert this mapping, but this mapping wouldn't be invertible in general. So we have a nice point, but we lose an aspect. So what we propose in this work is kind of a best of both worlds, where we'll use a kind of hierarchical design in terms of the embeddings, which will kind of have the advantages of both methods. And again, the kind of intuition beyond this is that we want to maybe have like different levels of granularity. And here, like from an intuition perspective, we call this fine and coarse, where our intuition is that the audio and the video are more fine-grained, whereas the text is more coarse. So we first learn an embedding for the video and audio, this kind of fine space. And then on top of that, we learn another mapping that goes from this space to the text space, which is the coarse space. And we call this kind of mapping fine and coarse. So this kind of things now respects the specificity of modalities because we have two different spaces to compare the pairs of modalities. But it also enables the different modalities to be easily compared, because if you want to, for example, compare audio and text, you can embed the audio in the fine space and just use this kind of projection ahead to go in the coarse space. And also, it turns out that in our kind of results, it's also the one that leads to the best results in the downstream tasks we consider. So this kind of maybe aligned to the kind of intuition we have about this. So to kind of train those networks, we want to do it again in a self-supervised way. So using kind of do not use like specific annotated data sets for that. So we use the How-to-100M data set that Gedas talked about before, that we had introduced 2 years ago, and also the audio set data set. So the How-to-100M data set has kind of text and video because it has been really focused around automatic speech recognition, where people describe what they are doing, whereas the audio set data set is more around like video and audio, but does not really have like speech into it. So to learn from those, we will need to kind of have a loss for that. And for that, we'll kind of use contrastive losses. And in this particular setting, we will have a sum of two losses. So the first one will be a video audio loss, and the second one will be a video text loss. And as I said earlier, I was saying that we won't have like direct audio and text pairs because in our case, what we want to really leverage is not necessarily learn to do automatic speech recognition, but we really want to kind of relate the sound of the objects with what's happening in the videos. And since our text comes from automatic speech recognition, we decide not to use an audio text loss because we just don't want to learn the speech recognition itself. So that's why we don't have explicit kind of audio and text pair, but we'll still be able to learn, as I will show later. So to learn relations between those two modalities, even though we don't have explicit training pairs. And we'll have, so those two losses that we consider, we'll use, for the audio loss, we will use a simple contrastive loss, which is basically, so maybe you're familiar with it, this kind of loss where you have a positive pair on the numerator with this exponential. And then we'll have some negatives that we will sample by, for example, taking video and audio from different videos. And so we will learn from this loss. But for the video and text loss, we use the MIL-NC loss, that is a multiple instance learning version of this loss that was introduced by one of our papers from last year. And the idea behind this loss is that usually the text and the video are not always aligned together, because people might describe things that do not happen exactly at the same time. So this is kind of an extension of the noise contrastive loss to deal with this kind of multiple instance learning scenario. And we basically train all of those networks from scratch on the out-to-the-runtime data set and the audio set. And before going into the quantitative results, I'm going to show you the kind of resulting spaces that we have with some qualitative examples. So one thing we can do is, after the model has been trained, to look for its ability to relate audio and video. And for that, we can, for example, take a sound that I will play now and look at the closest videos it retrieves in a dataset. So I'll play the sound. Play it again. So you can see this kind of sound of water and also a bit of some people, and then it retrieves people walking in some water. We can also take sounds of instruments like this one. So yeah, if you recognize, it's a didgeridoo, and the retrieve video are indeed closed from this kind of audio. But our models can also be used to retrieve from text to video. So for example, you can input text such as this sentence, add fresh chopped tomatoes and steer, and this is what the model will retrieve on. And I have to say that those videos were not seen during training, of course. You can do the same, pour some oil into a hot pan, and those are the kind of videos you will retrieve. But what's interesting is that we can also compare text and audio, even though we never train with those pairs together. So again, to do that, we use our kind of hierarchical spaces, where we'll first embed the audio in a kind of fine space, and then use the head that was only trained with videos to project to the core space where the audio can be compared with the text. And then now, given a text query has input such as airplane, we can also retrieve among a set of audio signal, also things that were not seen during training, such as airplane. Or chirping bird, for example. And so, yeah, that shows from a qualitative standpoint that we were able to also learn text to audio link, even though they were not seen together during training. But so those qualitative examples are nice, but of course we need to also show that the representations we learn are of high quality. And for that, we use a standard setting of self-supervised learning, where we train the kind of representation in a self-supervised way, and then we evaluate on different downstream tasks. And in that case, we focus on action recognition, on the HMDB51, the UCF 101, and the Kinetic 600 benchmark. We can also evaluate the audio representations, and for that, we use the ESC50 dataset and the audio set dataset. So first, just a quick look at the different embedding graph design. So as I said before, overall, what we've observed is that the fine-end course was overall the best if we consider all the benchmarks, compared to the different other options we've considered for the embedding graph design. Also, another question which was important is do more modalities help for learning? And so basically, we look into learning only from video and text, or only from video and audio, or using the three at the same time. And we see a gain by learning from the three modalities at the same time, which kind of comforts us into this idea of leveraging multimodal data. Also, comparatively to prior work, we are also, at the time of publication, state-of-the-art on the UCF 101 benchmark, when you kind of fine-tune the representation, as well on the HMDB51 benchmark. In terms of the audio, we were also state-of-the-art on the ESC50 dataset, which is a classification dataset for audio. And in the paper, we also consider benchmarks beyond those kind of small-scale datasets, which are UCF 101, HMDB51, and ESC50, as they start to saturate as a benchmark for self-supervised learning. And for that, we explore two larger-scale benchmarks, which is the video dataset of Kinetic 600. And we kind of set the first kind of point there with a linear performance of 70.5 top-one accuracy. which was at the time beating the previous published self-supervised method by a large gap. Similarly, for the audio, we also evaluate on the audio set dataset, where we obtain also the state of the art at the time. And in general, we encourage people to kind of use those new benchmarks for their self-supervised technique. Okay, so that was kind of the first list of the versatility, but I also said that I wanted to be able to kind of apply our video models on images. And for that, what we are going to do is to introduce something that's called network deflation. And so again, the motivation is that we want to be able to transfer from video and images in the same way that humans do. And in general, like most work in the community, consider learning first from images and then apply to video. But we think that we are in an era where there are much more data in a video form to leverage, like YouTube is huge, for example. So it could be that learning from video and then transferring to images might be better in the future than doing the other way around. And what we want is that we want to be able to apply our models that we've trained on video off the shelf without training on images. And we also want those models to be efficient when applied to images. So I guess you are all familiar with a technique which we call like inflated input, when we want to run a video model on an image input, where you can just repeat the image in time to kind of create a video that is a still video, where you can run your video model. But this is not efficient, of course, because you are repeating a lots of operation. So instead, what we propose is to deflate the network. So if you have, for example, a 3D convolution network, we'll render it into a 2D network so that you can run efficiently on an image. But so when we did so we tried to deflate the 3D convolutional kernels into 2D by summing along the temporal dimension. But we observed that there was large discrepancies between doing this and the kind of previous expensive method of inflating the input. And we found out that this was due to kind of the temporal padding effect that are present in 3D networks. And we addressed this issue by simply retraining the batch normalization parameters, gamma and beta, in a self-supervised way on a video dataset, where we basically try to compare to train those parameters so that they match the inflated inputs, vector. And we do that once, and then our model is ready to be run on images. When we do so, we kind of then evaluate our representation on the Pascal dataset and on the ImageNet dataset. And there are a few things to take out from this graph. So the first thing is that when you do this kind of naive deflation without this trick of renormalizing the batch norm, you get pretty poor performance compared to when you inflate the input. But with our proposed technique, we kind of match the kind of input inflation technique, but while our networks are much more efficient. And also a nice thing is that we compare to the performance of our networks with a method that has been trained supervised on kinetics, and we see a large gains from just using no labels basically, but just with this self-supervised technique. So we do outperform this. But we are still below kind of specific techniques that train on images. So there is a nice gap, to fill for us, and that's, I think, a nice challenge for the community in general. Cool. So let me wrap up the first part. So the key takeaway is that we propose a general framework to learn representations by aligning modalities, and we achieved state-of-the-art results for self-supervised learning on several downstream tasks. And we propose one step towards transferring from video to images, which we believe is an important kind of endeavor. And also we introduce potential new applications for which we only have qualitative results, such as zero-shot text-to-audio retrieval. So it will be nice to have those kind of benchmarks in the community. So we've made our models available both in TensorFlow and JAX. And so, yeah, I guess we'll share the presentation afterwards, and you will have the links. So this kind of concludes the first part of my talk, where we kind of design those versatile networks that can run on multiple modalities. And now I'll present the work more on the power side, where we want to only focus here on the vision and the language, and we want to kind of improve the models we had before. So in particular, in the previous work, the way we were comparing the modalities was very simple. We were only doing a dot product at the end of some networks. So there are potentially better ways to do this. Because, for example, if you have an image or a video, you might want to look at specific part in the image, and so you don't want to pull everything into a single vector. So the research questions we will have here are like how to enrich the interaction between modalities, and that will be done on the vision and language side. And can we still keep these networks efficient and fast, even though we want to enrich the kind of comparison of modalities? And again, we will look into the language-based visual search. So that will be the task of interest in this work, where given a text query, you want to retrieve from a large collection of images or videos a matching image or video. Such as a dog riding a bike on the street, you have your large collection of images and you want to retrieve that one. And for that problem, there are basically two kinds of approaches. One is called this dual encoder, which looks very similar to what I described in the previous approach, where you will embed your image on one side with a vision encoder and obtain a single vector. And then you do the same with the text, so you get a single vector and you compare the two with a simple dot product. And on the other end, there are the vision text transformer that instead of having this simple dot product at the end, they will kind of merge the two modalities with transformer. So as we saw in the previous talk, we will have like attention mechanism between the image and the text, which will enable a much richer score, which will, of course, be better. And this is what we observe in practice. So if we look at the current state of the art trained on similar amount of data, on existing benchmark, vision text transformer outperform dual encoder approaches. But one issue with one valuable aspect of dual encoders, even though they are a bit less performant, is their scalability in terms of large-scale search. So in fact, text and image embeddings can be pre-computed beforehand, indexed, and then used for large-scale search using matrix multiplication or approximate nearest neighbor search, which enables like sublinear search time. Whereas in contrast, to perform a search with a vision text transformer, one needs to apply an expensive transformer for each pair of text and images samples at test time. And so this does not scale well because it basically scales quadratically with the number of pairs you want to compare. So in this work, what we want is to basically get the best of both worlds. So we want to have a model to use the slow model, like to have like very strong performance for retrieval, but they are very slow. And we also want to have like fast network that are not as good for retrieval, but they are super fast and they are indexable. So we want to find a way to kind of get the best of both worlds. So for that, in particular, in our experiment, we use this instance of dual encoder, which uses a ResNet for the vision encoder on images and the bag of word for the text encoder. And we will call throughout this talk the fast model in this presentation. So we get a score with a simple dot product. For the vision text transformer, we propose an approach that starts from the image, run a standard network, and then upscales the feature map, similarly to what is used in object detection. And then we use a transformer decoder, similar to what has been introduced in Virtec, that can attend to this high-resolution map and kind of produce a score of similarity between the image and the language. And this kind of architecture enables richer cross-attention because you can attend to very large input images. But also the con aspect is that it's now much slower. But again, like what we want is we want to get the best of both worlds. So we propose two complementary ideas for that, so which are distillation and re-ranking. So the idea is to improve the fast model by distilling the knowledge from a vision text transformer, and later at inference, we use this to improve the model to retrieve the most promising elements given a text query. And so these top retrieved elements are then re-ranked using the slow model to improve precision. So now I'll just dive a bit into the details of how we do distillation, so how we transfer knowledge from the vision text transformer to the dual encoder approaches. So the idea is that during training, we are going to use the vision text transformer that produce very high quality scores for image and text, and we'll kind of try to transfer this into the dual encoder. So how do we do that? So at training, given a text query, we sample a fixed number of images, one of those being the ground truth. Next, we use the student dual encoder to output similarity scores for each image text pair using the dot product mechanism. Then these similarity scores are converted into a probability distribution using a softmax. Then in parallel, we also run the teacher vision text transformer to output its own distribution over those pairs. And then we finally just use a cross-entropy loss to kind of do this distillation from the vision text transformer to the student, the fast dual encoder. And yes, so now, given the distill model, what we can do is try to use that distill model to kind of improve the speed of the slow model. And so for that, what we first do is that we use our fast model to retrieve some elements, but a fixed set and a small set of those. And then we use the slow model to re-rank those scores. So for example, in this example, we start from a large collection. We retrieve the top 3, for example, with our fast model, which is very fast. And then we only re-rank those 3 with the slow model to get the final good results. And basically, now the question is, like, from this idea, can we get the best of both worlds? And for that, we train the models on the COCO dataset, captioning dataset, and we test them on the COCO for retrieval. And in this plot, the x-axis represents the time it takes to retrieve an image, and the y-axis represents the performance, so the retrieval at 5, which is basically the number of times the correct image is retrieved in the top 5. So now, our fast model, which only uses dual encoder, scores around here. And our slow model is much better, but is also much slower. As you can see, so we go from almost instant time for retrieval to 20 seconds. Now, if we distill the slow model into our fast model, we can improve the fast model significantly while keeping the same speed. And now, if we use the re-ranking technique that I described, we kind of basically match the performance of the slow model, but we reduce the search time by 100. And achieving kind of the best of both worlds we are targeting. So in this workshop, we are interested about videos. So what about videos? So actually, we show in our work that we can simply adapt the architecture we proposed to a video model, which is the temporal shift network applied on the ResNet dataset. And where instead of having a single like HW attention map to attend to, we will have a T times H times W attention map. And our architecture can also scale to those to this kind of spatio-temporal feature map. And equipped with this architecture and this idea of combining the fast and the slow model, we obtain state-of-the-art performance on the VATEC text-to-video retrieval dataset. So now let's just share the key takeaways from this work. So we kind of explore two complementary mechanisms to have both a powerful and a fast model. And those two mechanisms are distillation on one hand, where we take a slow model and try to distill its scores into a fast dual encoder approach. And then we have the re-ranking idea, which takes a fast dual encoder to kind of find some promising candidate that we can then rescore with a slow model. But since we have much less pairs to rescore, it's much faster. We also introduced this kind of language to vision attention architecture that's enabled to scale to high resolution feature maps. Finally, we show that this architecture works well on both images and videos, which kind of relates to our kind of versatility argument from the beginning. And we establish a new state-of-the-art on retrieval on the VATEC dataset. So if you are more interested about this paper, we have our poster on Wednesday, so feel free to come to answer more, to get more specific details. So with that, I'll just conclude. So I've presented two works that we are trying to go towards more multimodal models. So the first one was trying to leverage large-scale data sets of unlabeled videos to learn representations by learning from both vision, audio, and language. In the second part, I try to show how we can go towards richer interactions between modalities while keeping those models very fast and usable for retrieval. And with that, I'd like to thank you all for your attention, and I'd be happy to take some questions.
Thank you, Jean-Baptiste. Really, really interesting work. All right, so let me check. We have one question from the audience. I think this relates to the first part of the talk. They asked, do you think that the adaptive modality learning, i.e. learning which modalities to learn from for different parts of the video, may improve results even further?
Yeah, that's, I think, a really good question, because I think one big challenge with learning from from those large uncurated data sets is that there is a lot of noise. Sometimes, for example, that was what we observed in the auto-random data set, that there are lots of pairs where the vision and the text will not relate at all. So yeah, I think this relates to this question, because you want to have models that are able to kind of discard examples that are not useful for learning. So yeah, I do believe that using adaptive techniques such as those ones and kind of be able to bootstrap from your first model to kind of explore what are the best pairs you can use to kind of improve further is a very good avenue for future work. So I think there are some work that start to appear in terms of filtering, for example, the data sets beforehand, and then learn only on a curated data set. But I think, yeah, going for more adaptive techniques will improve results further, I think.
Awesome. I have one question that is a bit generic in terms of direction for self-supervision. So we all have the intuition that we can improve by just using more modalities. Given that the text modality that you use in these approaches that come from YouTube 100 million are kind of coming from a curated data set, do you see a way that we can get around that curation idea to use text from speech directly in things that are not related to the how-to videos?
Yes. So yeah. So first of all, I would say that I don't consider how-to as being curated in the same sense as, for example, kinetics, because so when we collected how-to, it was a very automated process. So basically, just to remind people, so what we did was to go on WikiHow and find name of articles and then query YouTube for those tasks, and we kind of get a large data set thanks to this. So it's not as curated as, let's say, kinetics. But I think I do agree that your question is interesting. I guess you are wondering, could we learn from just single modalities, for example? So have a big data set of just audio with speech, a big data set of video, and maybe still being able to relate those a bit similar to what happens, for example, in the unsupervised machine translation domain. And yeah, I agree. I think that's that would be really, really nice. And in some sense, in the work I presented, we had this kind of learning a bit through the vision common modality. So we could learn from, so audio set, for example, had no language, but we could still learn to improve the models by just using the video and audio link. So I think that's one possibility. So to be able to have models that only use pairs of modalities, but that do not need all modalities at the same time. So already with that, you can go a long way. But yes, I agree that you could also just train self-supervised on the audio alone. For the data sets, you have only the audio, and that should also improve the representations. But I think going towards a real kind of unsupervised linking of modalities with just sets of pure videos on one side and pure audio on the other side is very challenging, and more challenging than in the language domain. So I would still bet of having a bit of paired data sets for now.
Definitely, definitely. Another question from the audience. Gerard asked, do you believe handling structure in language instead of just sampling nouns and verbs could provide better, more comprehensive representations?
Yeah, I think that's a good question. So I guess that relates a bit to the kind of models we use for language in those work that are very simple, that are just kind of bag of words where we almost just average the words together, whereas now we know we have much more powerful models in language, such as transformers. And And basically, in our experience, I think on how to, it was always disappointing that as soon as we were going to like more complex language models, the results were kind of worse. And we had a few ideas why it would be the case. So the first one is that the language on this data set is very specific. So it's like people describing what they do, whereas we try to evaluate in a zero-shot manner on kind of more structured language data sets. And so we were afraid that when we use powerful language, I will use kind of almost overfit on the type of language that is used in the instructional videos, and then do not transfer as well on the downstream task. Whereas with like kind of bag of words model, they are kind of more robust in terms of domain shift. So that was one of our kind of potential explanation. But I think recent works like such as a clip or align shows that actually like using transformers for language can really improve the performance. So I believe it was more of a problem of a data problem than a kind of a modeling problem. And I do believe that having more structural language models should help in the future. And I think this is what we are going to see in the future.
Awesome, great. Do we have any more questions from the audience?
I do have one question. Well,
Go ahead.
I can give more time to the audience. So, and this relates to the first questions that was asked by the audience, like about handling noise across modalities, or like assuming that modalities are always aligned. So where do you see the direction going forward, right? So should we just rely on a scale, on larger scale, and try to come out, and let the scale alone help filter out those cases where there is no alignment? Or do you think it is important to investigate ways to detect those alignments in the video? So we mentioned a lot about the language, but there may be also a lot of misalignment from the audio side, right? So you may be hearing something that is actually off screen, right? And that may affect your learner, right? So yeah, I would like to know what's your perspective on this. Do you think like a scale alone can help out to filter out noise? Or do you think like, would it be a better direction, a smarter direction to try to come out with alignment techniques that helps you to predict whether there is alignment or not?
Yeah. So yeah, so first, I guess, so in our work, like this Milenci work from last year, we kind of proposed a very simple technique to kind of address this alignment issue by having this kind of multiple instance learning contrastive loss, which was basically taking not a single kind of video and align text, which might not always correlate, but look at kind of neighboring kind of text around the temporal segment you are looking at, and basically kind of only learn from one of those or like two of those, but not enforcing that they should all be aligned. And we did observe like large gain by doing that. So I guess my answer is that yes, I do believe we need to kind of address this kind of alignment issue, especially if we want to really scale to very large data sets where like the level of noise to the signal to noise ratio will be quite bad. So I think like better modeling is definitely one approach. And I think the other way to do it is also by curating the data sets. So yeah, how2 was kind of a curation technique because we targeted for instructional videos. And even though like the noise was pretty high, but it was like, yeah, I think if the noise is not too high and you have enough scale, I think it can learn. But I would still bet a bit on like just maybe finding other ways to find video and text from the web or video and audio that are better aligned. But yeah, I think in terms of the modeling side, another aspect that we have not really considered is like spatial aspect as well. So again, we were pulling everything together into a single vector, but maybe there is a way to kind of find alignment, spatio-temporal alignment between audio and video to kind of only learn from the parts that are kind of meaningful. And there, maybe like cross-attention could be one way to do this. Yeah. So I think, yeah, my answer is like not scale would not suffice alone. Like we would need like either modeling or better data curation techniques.
Thank you.
Awesome. I guess one last question from my side. Which modality do you think we should focus more on in your experience with dealing with all of these three modalities? Should we consider advancing the vision side of it, or the text side of it, or the audio side of it? which one is you think is lagging behind and making the performance lower than it should be?
Yeah, so I have to say, but it's maybe biased because this day I'm quite focused on more the vision and language part, and it's mostly because I'm quite excited to see the improvement in terms of language model that we've observed. But I think we are kind of lacking a very good examples of like, you know, relating those models to vision or audio. So yeah, it's not necessarily that we need to improve language, but we need to improve like the way we can relate those great language model with kind of audio or video signal. So yeah, yeah, but it's a personal taste as well that I think we can improve there. Basically, there is a leverage to use there.
All right, awesome. I think we don't have any more questions from the audience. So thank you, Jean-Baptiste, for a very great talk.
Thank you.
For the rest of the audience, we will have an afternoon session where we have two speakers, Carl Vondrek and Eugene True. It will start at 3 p.m. On Pacific time. We will use the same setup. We will have a Zoom webinar, and we'll also stream this on YouTube. So please join us at 3 p.m. Pacific time. Thank you so much.
Thank you. Bye-bye.
Thank you, Jean-Baptiste.